Hey, welcome everybody to the second module, radiation. We'll go ahead and get started. This is module 2. Here we're going to talk about jargon and black bodies. All right, so to start, let's talk about what we had last time. Last time was discussion on intensity. And the way that we started it off is looking at the heat flow between an emitter and a detector. We use this equation here to describe it. It's a differential amount of heat flow is equal to the radiative intensity, which depends on wavelength theta and direction theta, or lambda rather, in direction theta and phi. Here's the intensity. Your wavelength. Theta and phi is your direction. And the idea there is you had to look then at, or take this but multiply it by the projected angle, dA cosine theta. So if I were to draw this out here, say we have an emitter. And over here is a detector. If we draw a line between the emitter and the detector, and we can fan it out a little bit. It won't let me do that. I'll do it with my hand. So we fan it out a little bit here. The idea is that this is going to be our solid angle, the omega. The normal vector points up. Then this is going to be theta. And the emitter has an area dA. And the heat flow, here's dq. Just to finish off the equation up here, it's going to be over some differential wavelength band d lambda, and then over a solid angle d omega. Okay, so this is what we had last time. So now what we're going to do is we're going to play with this a little bit, in that we're going to describe the heat flux per wavelength band per solid angle. So essentially what we're going to do is say the heat flux we know is dq over dA, right? But since it's per wavelength band, we're going to divide it by d lambda, and per solid angle is going to be divided by d omega. If we do this, we get I sub lambda E, lambda theta phi, and then just the cosine theta is remains. So let's give this a name and a symbol. So this is going to be E sub lambda, lambda theta phi. And there's a name for this. This is called the directional spectral emissive power. So that brings about a few different new jargon, and that's what we're going to spend a lot of time on in this module, is this jargon. So the first thing here is emissive power. So this is E. We use capital E for emissive power. This again is defined here as the heat flux per wavelength band per solid angle. Although in a general sense, we think of emissive power as the heat flux associated with emission, or having this little E here means this deals with emission. Right, and again, emission is what as radiation produced at a surface that leaves that surface. Directional spectral, we'll have to make a little table here to describe it. So here we go. So if we were to look at something that is directional, I'm just going to reiterate what we have here. There's our detector. Up top, here's our emitter down here. And basically, we're talking about a single direction. Right over this little solid angle d omega. So directional just means one direction. So the counter to that, or the opposite of it, would be hemispherical. Hemispherical essentially means all directions. So say, for example, if you have a little detector here, you're only detecting the emissive power, or again, the heat flux, leaving the emitter, going and hitting that detector, going in the direction of that one detector. It has no idea what the directional dependence of that emissive power is. However, hemispherical, what's going on is, imagine you have essentially a hemispherical detector that you just place over top of your surface. So again, if the normal vector is pointing up, it basically captures all the radiation leaving the surface. So you can say here then that this encompasses all directions. So in our case here, the directional spectral emissive power, the directional side of this means that you're only detecting it in one direction. And we see that with this d omega here in the denominator. All right. Another qualifier we saw is spectral. So let's talk about that. So spectral means essentially one wavelength, or we'll say one small wavelength band, we'll say, or one narrow wavelength band. And we saw that in one of the examples in the first module, where we took a very small band of wavelengths, and that's what the heat flow was measured over. And then the opposite of that would be total, which means essentially all wavelengths. So let's do a quick example here. And we're going to introduce a new element of jargon here as we do this. So we have this definition here of directional spectral emissive power. We know it's simply going to be the intensity times cosine theta. So we're going to introduce, maybe before I dive into it, I'll go ahead and give you one more bit of nomenclature here, or jargon. We have something that is diffuse. What that means is that intensity now becomes independent of direction. So in other words, I lambda E, lambda theta phi can be simplified to just being a function only of wavelength. So we'll say here is it's independent of direction. Okay, so what does that look like physically? Well, what this means is that if you have a surface, and so you have a little area right here, and you were to look at what the intensity is in all directions, it's going to be the same. So this is supposed to be a semicircle here, the best I can with this. But the idea is that I sub lambda E doesn't depend on direction. So this is the normal vector pointing up like so. So you see it's equal, the magnitude of the vector arrows is the same regardless of direction, regardless of, say, theta, from looking at it from the side here. But we know, though, that if you go up, you know that the directional spectral emissive power is this I sub lambda E, but you multiply by cosine theta. So what does that mean? It means if you were to make a similar sketch here, so again, this is I sub lambda E on the left. If we're trying to look at what E is, you know that the value of cosine theta goes to 0 when theta goes to pi over 2, and theta is measured from the normal. So if we were to put the normal, again, pointing straight up, then you get something that peaks in the middle, comes back down. So the values of the length of the vectors are going to grow as you get closer to the normal, and then it shrinks back down, and it's symmetric. So this is E sub lambda. And here it depends on theta and phi. Although if you think about it, since really it only just depends on theta. So that leads into the example. Let's go dive into this a little bit more. Here's our first example for this module. So example 1. So what is the hemispherical spectral emissive power? In terms of intensity for a diffuse surface. Okay, so let's start off by looking at this equation here. We'll bring that down. That's what we know at this point. So we know that E sub lambda equals the intensity times cosine theta. Now, if it's a diffuse surface, we know that lambda, or I rather, does not depend on theta and phi. So if it's diffuse, we can simplify this as E sub lambda is lambda, and since the right-hand side, since we know now this only depends on lambda, we see a theta here, but we don't see a phi. We can actually simplify the left-hand side too as being only a function of lambda and theta. Because I sub lambda E only depends on lambda, and then we have the cosine theta. Now, the other part of this is we're trying to find the hemispherical spectral emissive power. So what that means is we're trying to integrate over all directions. And the way we do that is we have to integrate over all solid angles for a hemisphere. So here we go. So what we're going to do is say E sub lambda, and it's going to be only a function of lambda, right? Because that's the spectral side of it. The hemispherical side means it doesn't depend on direction anymore. And what we're going to do is integrate over the entire hemisphere of solid angles. So we can do that. And so what we can do is stick in the equation from the right-hand side above. So it'll be I sub lambda E, function of lambda cosine theta, the omega. We know that I sub lambda E is independent of direction, so we can bring this out to the front. So this will be I sub lambda E lambda, and we're going to integrate over cosine theta d omega. And then we learned in the first module how to relate the solid angle d omega in terms of theta and phi, d theta and d phi. It turns out, when you go back and review it, it turns out d omega is the same as sine theta d phi. So if we simplify this out, we get I sub lambda E lambda, and we're going to first integrate over phi. And we know, again, from the example in the first module for integrating over a hemisphere, phi is going to go between 0 and 2 pi, and theta is going to go between 0 and pi over 2. Cosine theta, sine theta d phi. Now it's just a matter of doing a little bit of calculus. So E sub lambda now is equal to that intensity. And then if we integrate over phi, we just get 2 pi. Now we're just integrating over theta. It's cosine theta, sine theta d theta. And so what we'll need to do here is a u substitution. So we'll say that u equals sine of theta, du equals cosine theta d theta. So all this together then gets you, so sine of 0 is 0 and sine of pi over 2 is 1. And you get simply u du, which is going to be u squared over 2, evaluated from 0 to 1, which gives you 1/2. So in the end, what you get is pi times I sub lambda e lambda. So for any diffuse surface, the hemispherical spectral emissive power, E sub lambda, only a function of lambda, is just pi times that intensity, which also again depends on lambda. Right? And one other quick definition as part of jargon is intensity by definition is directional, but we can integrate over all the wavelengths and get a total intensity. So, and the same goes for the emissive power. So they have the total emissive power. This is the hemispherical total. All you're going to do there is you're going to say E is equal to integral of lambda going to 0 to infinity, E sub lambda, lambda d lambda. And then you have the total intensity. Is I, which only depends on theta and phi, will be the integral of lambda going to 0 to infinity, I lambda e, put an e right here, lambda theta phi, phi lambda. So that does it for the first part of this module. We're going to now dive into something a little bit deeper. So this is still, we're talking about generic surfaces, things that aren't as useful for engineering calculations at the moment. This is kind of the fundamental definition side of things. Where things start to get a little more useful is when we put everything in terms of a black body. So a black body is a perfect emitter. But just like in thermodynamics, for gases, we often like to use the ideal gas law. It's an idealized approximation of gases that makes life a lot easier for doing engineering calculations. Same thing is true for this. This is an idealized approximation to the behavior of a surface. And when we get into the third module, we'll start talking about how we can basically use the black body as a basis and then modify our calculations based off of it. So here we go. So what is it? There's really two ways you can think of a black body. So the first way is, imagine if you have a very large, say, volume that is enclosed with a little opening here, and say it's perfectly insulated and has some temperature T. So it turns out that the leaving radiation is pretty close to a black body, which I'll use as B body, at some temperature T. In other words, you have a lot of radiation bouncing around inside this cavern, if you will, and that little opening there, what's coming out is really close to a black body at that temperature T. The second way of thinking about it is a really big medium. At some temperature T. And two common examples for this is outer space. which is somewhere 2 to 4 Kelvin. And the other one is the deep ocean. So say a very, very deep body of water. So the idea though is that for practical engineering calculations, a black body doesn't exist outside of these. So we have to come up with a way to work with non-black bodies. And again, what we do is we start with the black body as the ideal, and then we modify it, or we have a multiplying factor on it. All right. So what are the properties of the black body? Well, one is that it has to be diffuse. All right, we already talked about that. And the second is that the intensity, and now I'm going to modify that little e here to now be a b. It's a little bit of a difference. So this little b here now stands for black body. And I'm going to put a t on here as well, because we can directly relate it to t, because this intensity follows what's called a Planck distribution. So in other words, as long as we know the temperature, we know how the intensity varies with lambda. It's a very powerful thing to know. And all of a sudden, we can start doing more useful calculations. All right. So the Planck distribution, here, I'll just say that the product of lambda times t is very important. And it's very important for two reasons. So the first reason is something called Wien's law. And that is that lambda max times t is roughly 3,000 microns Kelvin. Okay, so what does this mean? So this lambda max is the peak wavelength emitted by a black body. Maybe we'll say this, emitted by a black body at temperature T. So I'll show you here a diagram of the black body. This is the spectral black body emissive power. But the idea behind this is that you have a wavelength here, and you have curves for different temperatures. And this is just out of the Incomparative book. But the idea here, as you can see, is that if you take the peaks, they all tend to follow along this straight dashed line in this plot. So I take the peak of this curve at 50, the peak of the curve at 100K, and so forth. You can see that that peak wavelength falls along this dashed line. Well, this dashed line here, you can see is lambda max T, and I said 3,000 microns Kelvin. The actual number is 2898, but for our purposes, for just rough calculations, 3,000 is just fine. The lambda max times T is 2898 micron Kelvin. Notice here the visible spectral region. So let's take a look, and we'll do an example where we'll check that out. So here we go. This will be the example number 2. So say the sun is approximated as a black body at 6,000 Kelvin. So what is the peak wavelength? Well, it's pretty simple. You just apply Wien's law. So it'll be 3,000 microns Kelvin over 6,000 Kelvin is about half a micron. And notice that half a micron is in the visible range, right? Because for the visible range, I got a little bit cleaner there. It's between 0.4 microns and 0.7 microns. And we can see that in here, right? We can see that that peak for 5800 Kelvin, again, roughly 6000 Kelvin, we get that peak in the middle of the visible regions of the electromagnetic spectrum, somewhere around 0.5 microns. So there's a 0.4 on the left, 0.7 on the right. So we're right there in the middle. And that's a very important fact. And one of the more interesting facts that come out of radiation is that over time, our eyes, just through natural selection, have evolved to be calibrated to the peak wavelength of the sun. All right, that's why in the visible spectrum, our eyes have been trained to see that wavelength really, really well. So it's a fun fact that I like to introduce in classes. Oops. All right, so that's the thing. That's the first part of this, this importance of lambda times t. But then there's something else that can be done. And the second thing that can be done is called band emission. This is, you can calculate out the heat emitted in a range of lambda. In other words, we can say here is that we'll do a definition here. We'll say f from 0 to lambda 1 is a function of time. And we'll define this then as the fraction of blackbody radiation emitted between lambda equals 0 and lambda, we'll call lambda 1, and it depends on temperature T. This definition is, you can write it as that we're going to integrate from lambda going to 0 to lambda 1, e lambda b, which again is a function of lambda and t. And we're going to integrate this over all of the blackbody spectrum. So lambda going from 0 to infinity. And we have e lambda b, lambda t, d lambda, right? So we're going to take the hemispherical total, the hemispherical spectral emissive power for a blackbody. And we're going to integrate it over all wavelengths. And that's what you get as our hemispherical total emissive power. And it turns out you probably know what this is. This is E sub v, right? Our hemispherical total emissive power, which is sigma t to the fourth. Where sigma is the Stefan Boltzmann constant. Easy thing to remember because it's 5, 6, 7, 8. So 5.67 times 10 to the minus 8. And the units in SI are watts per meter squared Kelvin to the fourth. All right. Now, one other fun thing you can do is, we already know that blackbodies are diffuse surfaces. We've already, if you go way back here, we know that then this hemispherical emissive power is equal to pi times the intensity. So hemispherical hemispherical spectral emissive power is pi times the blackbody intensity. So we can also set this equal to lambda equals 0 to lambda 1, I sub lambda e, and you can put the pi out front. Actually, this will be, instead of e, it'll be a b. And down below here, we have a pi 0 to infinity, I lambda b lambda t. And so just by comparing these two equations here, you can see then that in order for the denominators to be the same, they both have to be sigma t to the fourth. That means that if you integrate the blackbody spectral intensity, we must get sigma t to the fourth over pi. So the pi's cancel out. So just a fun fact there. All right, so there you have it. So you have the fraction of black body radiation emitted between a wavelength of 0 microns and lambda 1. That's going to be this integral up top divided by sigma t to the fourth. And it's something that somebody has already done, and you're provided with these values of the band fractions as part of the equation sheet for the qual. And here you go. Again, there's a known relation and somebody's already done the work for you. The idea is that you take the product of lambda and t, and from that you can get the value of this band fraction f. If you're curious about what the intensity is, you actually can calculate it out directly. You take this number here and you multiply it times sigma t to the fifth, and then therefore you get your intensity, your spectral intensity. And then you can also look at the radiation of this I sub lambda b versus that for the maximum, that peak wavelength. And notice that they shade here 2898 because by Wien's law, lambda max times t equals 2898 for the peak wavelength. So let's go ahead and apply this here as our final example. So example 3. So what fraction of sunlight is in the visible range of the spectrum? Well, okay, let's see here. So what we're trying to find is the fraction from, say, lambda 1 to lambda 2, and we're going to take the sun again, approximate as a black body, as t at t sun. And we know a couple things here. We know that lambda 1 is 0.4 microns, lambda 2 is 0.7 microns, and t sun is 6,000 Kelvin. All right, well, what we're trying to find here is the integral from lambda 1 to lambda 2 of our black body spectral emissive power, all divided by sigma t to the fourth. Okay, well, we don't have a direct way to get this with the band fractions, but I hope you can see that since we're just integrating a region, a band, this is the same thing as integrating from 0 to lambda 2 minus the integral from 0 to lambda 1. And again, we're going to take it over sigma t to the fourth. Go ahead and insert a page here. All right. So therefore, what you can see then is that f from lambda 1 to lambda 2 at t sun is equal to f from 0 to lambda 2 at t sun minus f from 0 to lambda 1 at t sun. Okay, well, how do we get lambda, what these fractions are? Well, remember, it's the product of lambda times t. So lambda 1 times t sun is equal to 0.4 microns times 6,000 Kelvin, which gets you 2,400 microns Kelvin. Lambda 2 times t sun is 0.7 microns, 6,000 Kelvin is equal to 4,200 microns Kelvin. Okay, so now that we've got our two magic numbers here, 2,400 microns Kelvin and 4,200 microns Kelvin, let's go down to the tables. All right, 2,400 micron Kelvin. Here's our value here, and our fraction is right here. So it's going to be a 0.14. .140. All right, so then 4,200 microns Kelvin. Go further down, we're right here. 516. So therefore, f from lambda 1 to lambda 2 at t sun is equal to 0.516 minus 0.140, which gets you 0.376 or 37.6%. So in other words, we see roughly 1/3 of the actual amount of radiation coming out of the sun. So even though our eyes, again, have evolved over time to be able to see the sun as best as we can, we still only see about 1/3 of it. We don't see a lot of the outside of that band. And just to finalize the point, if you go back to this plot here, again, the visible region is this part here. We see, it's tuned for this peak amount. We see it quite a bit, but you can see there's definitely a part both to the left of it here in the UV and to the right in the IR that's not captured under the integral of this entire curve. So again, we only see about 1/3 of it. And that's it.